Deep inside the universe's most mind-bending mysteries, there lurks a paradox so wild it defies everything we think we know. White holes, the cosmic fountains that spew what black holes swallow. Imagine a place where the impossible becomes reality. Shimmering vistas of shimmering light spiraling into endless horizons. Yet somehow, nothing stays the same. In this video, we're venturing into the unimaginable, where AI conjures surreal visions of what lies beyond the event horizon, revealing a universe that's strange, beautiful, and absolutely impossible to ignore. Buckle up, because this is the uncharted edge of reality, and the journey is nothing short of extraordinary. The concept of white holes in modern physics. White holes emerge as tantalizing counterpoints to black holes within the framework of Einstein's general relativity. Unlike black holes, which relentlessly trap everything including light, white holes are theorized to spew out matter and energy, acting as cosmic fountains or vents expelled from the fabric of spacetime itself. Conceptually, they could be regions of the universe that nothing can enter, only exit, the cosmic equivalent of a one-way gate that refuses entry but showers the universe with matter and radiation. This idea arises from solutions to Einstein's field equations that are time-reversal counterparts to black holes, implying a universe where the flow of time near a white hole is backwards, or at least fundamentally different from what we observe around black holes. Yet, white holes are plagued with paradoxes and paradoxical implications that stretch the mind. For instance, if a white hole exists, what prevents it from being swallowed by a black hole? Its temporal twin? Could the two form a closed loop, constantly exchanging matter in a cosmic dance, leading to a paradoxical cycle where matter disappears in one and reappears in the other? The notion also raises questions about entropy and the arrow of time. How could a white hole spew out matter without breaking the second law of thermodynamics? The idea seems to fly in the face of the universe's tendency toward disorder, creating surreal visuals of matter. Stars, planets, even galaxies, bursting forth from an invisible point in space, only to vanish again, leaving behind shimmering trails of radiation, like cosmic fireworks. Visualizing white holes is inherently surreal. Instead of the dark, swallowing maw of a black hole, imagine a luminous fountain, an otherworldly geyser erupting in space, showering particles and light across the void. Specks of cosmic dust could be flung outward in intricate patterns, shimmering against a backdrop of dark matter. Space itself might appear to ripple and distort around these phenomena, bending and twisting in ways that defy intuition. Some models suggest that white holes could contribute to mysterious bursts of gamma rays, fleeting yet intensely energetic phenomena visible across billions of light years. These are not just abstract concepts, but real, perceptible anomalies that challenge our understanding of causality, space, and time. Despite their speculative status, white holes ignite the imagination precisely because of their inconceivable nature. They suggest a universe where the flow is not merely inward but outward, contradicting everyday notions of creation and destruction. If they exist, they could be key to understanding wormholes, giving a theoretical bridge that connects different parts of spacetime, possibly even different universes, by spitting matter out in one region while swallowing it in another. The paradoxes and visuals swirl together, creating a mosaic of cosmic impossibility that humans have only begun to explore with mathematical equations and speculative models. It's a realm where the known laws of physics stretch, twist, and sometimes snap, revealing the limits of what the universe might be capable of, or what it might reveal if we dare to look beyond the black hole's dark shadow into the bright, impossible glow of a white hole. Historical origins and theoretical foundations. The concept of white holes emerges from the rich tapestry of general relativity and the intricate dance of spacetime. They are often described as the theoretical opposites of black holes, regions where matter and energy are expelled instead of drawn in. This notion traces its roots back to Einstein's field equations, which are the mathematical framework describing how mass and energy influence spacetime curvature. while black holes have been more thoroughly studied and even observed indirectly through phenomena like gravitational waves and accretion disks, white holes dwell more in the realm of mathematical curiosity. They represent solutions to Einstein's equations that hint at a universe with regions of explosive outward energy, defying the conventional notion of gravity's relentless pull. The source of these solutions can be traced to the Schwarzschild metric, one of the earliest exact solutions discovered for a spherically symmetric, non-rotating mass in vacuum. When extending these solutions, physicists considered what happens when a black hole's mathematical mirror image is constructed, a region where nothing can enter and everything is expelled. This led to the theoretical idea of a maximally extended Schwarzschild solution, which contains not only a black hole but also a white hole region, connected via a wormhole-like structure called an Einstein-Rosen bridge. Such bridges are speculative, conceptual tunnels connecting different parts of space-time, and they rely inherently on the mathematics of space-time topology rather than empirical evidence. Stepping into the realm of theoretical physics, the notion of white holes becomes entangled with some of the most perplexing paradoxes and surreal visuals of our universe. They conjure images of shimmering, radiant fountains bursting out matter and light into the void, creating scenes that are both beautiful and unsettling. Yet, thanks to the principles of causality and thermodynamics, white holes face significant theoretical challenges. They appear as unstable solutions that would quickly collapse or dissolve, prompting many physicists to see them as mathematical artifacts rather than physical objects. Nevertheless, their existence remains an intriguing aspect of the space-time landscape, provoking questions about what might lie beyond the limits of our observable universe or inside the mysterious depths of black holes themselves. The historical journey of the white hole concept is more intertwined with the evolution of relativity and cosmology than with direct scientific pursuit. Early solutions like the Schwarzschild metric didn't interpret white holes as real objects, but rather as illustrations of the mathematical possibilities allowed by Einstein's equations. It wasn't until later that their conceptual relevance emerged, partly inspired by the desire to understand singularities, wormholes, and the ultimate fate of collapsing matter. Thought experiments, often carried out by theorists envisioning possible universes or alternate dimensions, kept this idea alive. Today, advances in quantum gravity and string theory continue to explore how such paradoxical entities might fit into a broader, multi-layered understanding of reality, where impossible visuals coexist with the language of mathematics, challenging our intuition and expanding the horizon of what could theoretically exist within the universe's complex fabric. Distinguishing white holes from black holes. Fascinating contrasts emerge when examining the nature of white holes versus black holes, especially through the lens of their observable signatures and theoretical properties. Black holes, with their infamous event horizons, serve as cosmic vacuum cleaners, regions where gravity is so intense that nothing, not even light, can escape once crossed. Their defining feature is this event horizon that marks a point of no return. White holes, by contrast, are hypothesized as the universe's cosmic expulsors, sources that spew out matter and energy but refuse to allow anything in. This stark difference hinges on their fundamentally opposing roles in space-time geometry, yet distinguishing one from the other moves into a realm riddled with paradoxes and speculative physics. Despite the unsettling theoretical basis, scientists contemplate how one might observe or differentiate these objects if they existed visibly in our universe. Black holes often reveal themselves through accretion disks, bright, luminous spirals of infalling gas and dust heated to extreme temperatures, and through gravitational waves generated during mergers. White holes, on the other hand, are expected to constantly eject energetic jets in matter, with no accretion signs because, by their very definition, they don't swallow incoming matter. The challenge is that, while black holes are supported by a relatively large body of observational evidence, like the signals from gravitational wave observatories and X-ray missions, white holes remain purely theoretical constructs, circling in the domain of mathematical possibility. One of the most surreal visual distinctions arises from the potential appearance of a white hole. Imagine a cosmic fountain of shimmering, high-velocity particles erupting in all directions against the darkness of space, contrasting sharply with the darkness of a black hole's shadow. While black holes cast an ominous silhouette, white holes would manifest as luminous beacons, radiating energy with a brilliance that defies the normal flow of time and causality. Their edges might resemble a shimmering horizon of outgoing radiation. But the paradox is that such a source would seemingly violate the principles of thermodynamics and causality. Observing such an object could produce a dizzying visual experience, an almost unnatural display of matter bursting outward from an unseen and impossible boundary in the fabric of space-time. The crux of their difference also resides in the paradoxical nature of white holes. They appear to be the reverse of black holes in time, theoretically emerging from solutions to Einstein's equations that suggest they could be the flip side of a black hole's event horizon. Yet, no known processes generate white holes naturally. Their existence would challenge the arrow of time and raise questions about entropy and the flow of information. If a white hole were to be detected, it would be indicated by an energetic, outward-facing emission that contradicts the inwardly drawn gravity of typical cosmic objects, and it would stand as an odd mirror, an impossible, paradoxical reversal of the black hole's inward trap, a surreal spectacle that blurs the very boundaries of physical law. The science of singularity and event horizons. Black holes, often perceived as cosmic vacuum cleaners, contain regions called event horizons, boundaries beyond which no information or matter can escape. The concept of the event horizon encapsulates the core paradoxes of modern physics. Light itself struggles to escape the gravitational pull at the horizon, distorting space-time into a surreal fabric that warps and bends hopelessly beyond comprehension. Inside, space and time effectively trade places, with gravity so intense that they invert in strange, counterintuitive ways. To a distant observer, an object approaching this boundary seems to slow down and fade away, caught in a perpetual dance of redshifting, while from the object's own perspective, falling inward appears almost instantaneous. Yet both views coexist in a bizarre, contradictory harmony that defies traditional logic. At the heart of these phenomena lies the singularity, a point where our current understanding of physics collapses. Here, density compresses into an infinite point, where space-time curvature becomes infinitely steep. The laws of general relativity predict this collapse, but they give no account of what truly happens, only that our equations break down utterly. This creates a paradox. The universe's most extreme gravitational well seems to contain a breakdown of the fabric that sustains reality itself. Many theorists see the singularity as an invitation for new physics, perhaps quantum gravity, to step in and rewrite the rules. Bridging the gap between the smooth, continuous spacetime of Einstein and the probabilistic world of quantum mechanics remains one of the greatest intellectual pursuits, with ideas like string theory and loop quantum gravity offering tantalizing hints but no definitive answers. The concept of a white hole, a hypothetical reverse of a black hole, pushes the mind further into surreal territory. While black holes are regions where matter gets swallowed and cannot escape, white holes are envisioned as cosmic fountains that spew out matter and energy. If such objects exist, they might be connected via wormholes, a kind of cosmic shortcut that links distant points in space-time. This interconnected web hints at a universe that is fundamentally nonlinear and paradoxical, where information might escape one boundary only to emerge in ways incomprehensible to our current laws. The event horizon of a black hole resembles a surreal, glowing boundary, but in the case of a white hole, it's a violent eruption of what had once been hidden, giving the impression of an impossible, alien topology where causality itself might be compromised. These visions challenge not just physics, but the very notion of cause and effect, hinting at a universe more like a wonderland of paradox than a deterministic clockwork. Ultimately, the science of singularity and event horizons plunges us into a realm of cognitive dissonance and extraordinary visuals, where space-time contorts into impossible shapes, black holes swallow entire stars, and the fabric of reality seems to unravel into pure potentiality. These phenomena sit at the crossroads of what is known and the unfathomable. They compel us to consider that our universe might be more fluid, more mysterious than the neatly ordered cosmos we inhabit. Inside a white hole, if they exist, we would see a landscape so far removed from everyday experience. An endless fountain of creation blazing with surreal clarity, a testament to the mind-bending interplay of physics at its most extreme and enigmatic. Mathematical models of white holes. Theoretical explorations of white holes lean heavily on the fabric of general relativity, where Einstein's equations allow for exotic solutions that defy conventional understanding of spacetime. Unlike black holes, which are well supported by observational evidence, white holes exist primarily as mathematical curiosities, solutions that emerge naturally from Einstein's field equations but lack direct empirical confirmation. These models suggest a region of space-time that aggressively expels matter and energy, essentially the time reversal of a black hole's inward collapse. Intriguingly, when scientists attempt to craft mathematical frameworks that incorporate white holes, they encounter paradoxes and instabilities, revealing just how fragile these constructs are within the classical regime. Key to understanding white hole models are solutions like the maximally extended Schwarzschild spacetime, which contains a white hole region hidden within a more complex manifold. These solutions often feature a bifurcated event horizon, one for black holes and one for white holes, connected through a hypothetical wormhole or Einstein-Rosen bridge. Yet, the stability of such models is deeply questionable. Small perturbations tend to turn white holes into black holes or cause them to decay into singularities, highlighting their delicate nature. In some models, white holes act as cosmic fire hoses, spewing out matter infinitely fast, generating surreal visuals of jets of energy and particles flowing outward, impossible to contain or predict with certainty. Mathematically, the challenge revolves around encoding these entities in the language of differential equations. Classical relativity relies on boundary conditions at horizons, but white hole solutions require conditions that destabilize or violate typical energy constraints. For instance, some models attempt to impose conditions where the horizon's outgoing flux is infinite or ill-defined, creating a paradoxical situation where the universe appears to overflow with matter from a point of no return. Advanced models incorporate quantum effects, like Hawking radiation analogs for white holes, adding layers of probabilistic mathematics that push the models into surreal, often non-intuitive realms. These quantum considerations attempt to stabilize white hole solutions, but often lead to bizarre predictions of space-time fluctuations that resemble fragmented, shimmering textures of reality. Each fluctuation an improbable portal of chaos and wonder. The very idea of a white hole involves a kind of reverse causality, matter escaping in a manner that violates normal entropy trends and thermodynamic expectations. As such, mathematically modeling these entities often skews toward violations or reinterpretations of known physical laws. Paradoxes arise where information appears to vanish from our universe or emerge from a hypothetical hyperspace, dramatically challenging notions of causality. Visualize the equations as surreal sculptures, twisting symmetries and abrupt irregularities that defy intuitive understanding. Each solution a flickering mirage of what might be possible in a universe unfettered by classical constraints. The pursuit of these models fuels a tantalizing hope that perhaps, hidden within the equations, lies a deeper understanding of cosmic symmetry, or even a glimpse into the fabric of realities where the impossible becomes merely a different form of the fathomably strange. Quantum mechanics and white hole stability. Quantum mechanics introduces a realm of possibilities that challenge our classical understanding of the universe. especially when it comes to entities like white holes. Unlike black holes, which are somewhat established as cosmic sinks swallowing matter irreversibly, white holes are theoretical constructs that emit matter and energy, seemingly defying the second law of thermodynamics. The idea that white holes could exist stirs up a myriad of paradoxes. How can something spontaneously erupt into existence and remain stable without collapsing under their own gravity? When you delve into the quantum properties of space-time itself, the picture becomes even more surreal. Quantum fluctuations near the hypothesized boundary of a white hole would imply that the event horizon is not a static feature, but a dynamic, unstable membrane, flickering between existence and annihilation. The stability of white holes faces profound challenges rooted in quantum mechanics. Hawking radiation, famously associated with black holes, hints that quantum effects allow for the gradual loss of mass and energy. For white holes, the opposite process could occur, an influx of particles from seemingly nowhere, generating a feedback loop that threatens to destabilize their structure. These quantum emissions resemble the emission of ghostly, probabilistic energy packets, which, in theory, could cause a white hole to flicker or even evaporate completely. Simulations within semi-classical gravity models suggest that white holes, if they exist, would be inherently ephemeral, collapsing almost as swiftly as they appeared, leaving behind dangerous, unstable space-time regions akin to quantum foam. Surreal visuals emerge when considering how quantum mechanics might govern their interiors. Instead of a smooth, predictable boundary, a white hole might manifest as a shimmering, kaleidoscopic surface, an oscillating membrane of energy pulses that flicker in and out of existence, governed by the strange probabilities of quantum superposition. Here, classical notions of stability unravel, replaced by chaotic dance of entangled particles and quantum interference. The interior might warble with virtual particles streaming in and out, creating a constantly shifting environment that challenges the very concept of a well-defined, stable lumen. Efforts to reconcile the stability of such an entity often invoke hypotheses about quantum gravity, suggesting that perhaps only a full theory, beyond current models, can predict whether white holes are mere mathematical curiosities or cosmic fixtures. Most intriguingly, the paradoxes they suggest deepen when considering their relationship with black holes through the lens of quantum entanglement. The idea of white holes as time-reverse black holes leads to mind-bending questions. Could a white hole be the final act in the life cycle of a black hole? Or are they fundamentally incompatible with quantum mechanics' insistence on unitarity, the preservation of information? Some theories propose that quantum entanglement might stabilize a white hole by linking it to black holes elsewhere in space-time, creating an entangled bridge of sorts that prevents catastrophic decay. But these visions remain speculative, largely because the quantum mechanics of white hole stability pushes the boundaries of known physics, inviting us into a realm where logic blurs and the impossible becomes a tantalizing possibility. White holes in general relativity. White holes emerge from Einstein's equations as a curious theoretical flip side to black holes, born from the fabric of space-time itself. While black holes relentlessly trap everything that crosses their event horizons, white holes are their cosmic mirror images, objects that spew out matter, energy, and radiation rather than absorb them. Mathematically, they are solutions to the equations of general relativity that describe a region where nothing can enter, only exit, creating a surreal and almost theatrical spectacle in the universe's grand theater of possibilities. These entities challenge our intuitive grasp of causality and time, suggesting a universe where the arrow of entropy might have an unusual companion in these cosmic fountains. The intriguing paradoxes surrounding white holes lie in their very nature. If black holes are the ultimate sinks, then white holes would be their impossible antitheses, sources from which matter bursts forth without any apparent cause or origin. In theory, their existence implies a universe where information and matter emerge spontaneously, defying conventional notions of causality rooted in the forward march of time. Some models even indicate that white holes could be connected to black holes through hypothetical wormholes, forming a sort of cosmic shortcut or tunnel. A theory tantalizing enough to fuel science fiction, yet stubbornly resistant to empirical confirmation. This creates a mind-bending mental image, a universe where matter can appear suddenly from darkness, like flickering stars of pure potentiality. Visually, white holes are often depicted as luminous, tempestuous geysers in the void, jets of energy bursting out with incomprehensible ferocity against the black backdrop of space. Surreal visions suggest glowing spheres or spikes of radiation that expand outward in harmonic, yet chaotic patterns, reminiscent of cosmic fireworks, defying the natural tendency of entropy to increase over time. These visuals evoke feelings of otherworldliness, objects that seem to violate the fundamental flow of time, as if space itself has been twisted into unrecognizable shapes. Such imagery sparks a sense of wonder and curiosity, prompting questions not just about what they might look like, but about their very nature and existence in the universe. Despite their compelling theoretical beauty, white holes are not supported by direct observational evidence and are widely considered speculative constructs of Einstein's equations rather than concrete features of our universe. Still, their implications ripple through our understanding of physics, prompting debate about the fabric of space-time, the nature of singularities, and whether these imaginary objects could exist under some extreme conditions. They serve as a window into the tangled, counterintuitive depths of general relativity. The idea of a universe with white holes is as provocative as it is mysterious, forever pushing the boundaries of what we consider possible in the endless, surreal canvas of the cosmos. Speculative nature and scientific impossibility. The notion of a white hole bursts into consciousness from the folds of theoretical physics as an antithesis to the black hole, where instead of consuming everything, it acts as a cosmic fountain ejecting matter, energy, and perhaps even information. Yet, the scientific community regards white holes with a skeptical eye, primarily because they challenge current understanding of fundamental laws. They are prescribed as solutions to Einstein's field equations under certain conditions, but would require circumstances that defy observed reality, most notably, their instability. Unlike black holes, which form through gravitational collapse, white holes would have to spontaneously appear and eject matter without any clear origin, creating a paradoxical universe within the universe. This presents a surreal visual, a radiant, infinite burst of light, spewing matter into empty space that seems to defy causality and conservation laws. This speculative landscape makes the concept of a white hole an imaginative playground for physicists and science fiction writers alike. Pictures of a white hole often depict a vortex of shimmering energy, swirling outward in a chaotic dance of particles that seem to flicker between fragments of reality. These visuals evoke scenes from surreal art. Impossible waterfalls of starlight, where the flow of cosmic matter is one way, unidirectional, and entirely unstoppable. Such imagery, while mesmerizing, remains firmly rooted in the realm of conjecture because it relies on physical models that have yet to be observed or empirically validated. According to current science, the creation or stable existence of a white hole would violate the second law of thermodynamics, as it would produce order, an organized expulsion of matter, spontaneously, which is inconsistent with entropy increase. The core scientific challenges are profound. For a white hole to exist safely within our universe, it would need to be inherently unstable, potentially collapsing or collapsing into a black hole as soon as it forms. This instability makes sustained white holes a theoretical impossibility under current models. Some speculative ideas propose that white holes could be transient phenomena or portals connected to black holes through wormholes, imaginative constructs that stretch the fabric of space and time to their limits. Yet, even these concepts are riddled with paradoxes. How does information escape a black hole into a white hole, given the firewall and information paradox debates? The mathematics suggest that if white holes did exist, They would pose enormous contradictions when integrated into the fabric of space-time, creating a surreal landscape of anabaryons and antimatter nearly frantically bursting forth into reality. In some ways, white holes embody the very essence of scientific impossibility, improbably elegant solutions to gravity equations that clash with causality and thermodynamics. They symbolize the edge of human curiosity about the universe's true nature, standing as fantastical reminders that our grasp of reality, at least for now, remains incomplete. While science fiction often paints silvery visions of white holes as cosmic doorways to other dimensions or sources of limitless energy, actual physics treats them as unstable illusions. Still, contemplating their existence pushes the boundaries of what we understand about the universe's structure, an ongoing dance between the feasible and the fantastical. The result is a landscape of surreal visuals and paradoxes that challenges the imagination and underscores the profound mysteries lurking just beyond the horizons of scientific certainty. Potential signatures and detectability. Within the realm of speculative astrophysics, the signatures of a white hole, if such entities exist, would defy conventional detection methods, plunging scientists into a surreal realm of the impossible. Unlike black holes, which are characterized by their event horizons trapping light and matter, white holes are theorized to eject energy and particles with an almost paradoxical invocation of the universe's apparent symmetry. Their potential signals might be fleeting bursts of extraordinarily high-energy radiation, akin to cosmic fire hoses spewing forth jet after jet of gamma rays or 10th rays, but with a twist. These emissions could appear as sudden flashes, unlike anything produced by known astrophysical phenomena, perhaps showing irregular, asymmetric patterns that defy classical models. The challenge of detection lies not only in the exotic nature of white holes, but in their potential rarity and unpredictability. They could be transient, appearing suddenly and vanishing just as quickly, leaving behind hints faint enough to drown in cosmic background noise. Our instruments, complex arrays of telescopes and detectors, would need to recognize the surreal visual signature of an impossible ejection event. This might manifest as spectral anomalies, bursts with unusual polarization signatures, or even energy distributions that challenge current understanding of radiative processes. For example, a white hole might emit a sudden, directed beam of ultra-high-energy cosmic rays, forming a brief, intense corridor through the fabric of space-time, offering a flickering signature detectable by ground-based observatories or space-based gamma-ray detectors. Furthermore, the potential gravitational or quantum signatures could serve as indirect clues. If white holes exist, their influence on surrounding matter might be unlike anything observed near black holes, perhaps generating peculiar gravitational lensing effects or producing localized anomalies in the cosmic fabric. These signatures could resemble a paradox, where light appears to emerge from a seemingly forbidden zone, or matter is expelled with a velocity and energy incompatible with collisionless ejection processes. For example, unusual distortions in the cosmic microwave background radiation might hint at the energetic origins of these celestial portals, if such distortions could be carefully isolated from other phenomena. Detecting white holes, if they are even real, involves embracing the bizarre and the extraordinary, recognizing that their signatures might resemble a surreal language of the cosmos, one woven with paradoxes and alien visuals. Perhaps what we interpret as random high-energy bursts are in fact the ghostly echoes of impossible ejections, or the universe's way of teasing us with hints of a cosmic event that defies our common sense. These signatures would push current technology to its limits, demanding unprecedented sensitivity, resolution, and a readiness to interpret the impossible with an open mind. In doing so, we might glimpse a fragment of the universe's deepest, most surreal secrets, where the boundary between the conceivable and the unimaginable dissolves entirely. Imagining white holes through AI's lens. Artificial intelligence, with its capacity to process vast data sets and generate vivid visualizations, pushes the boundaries of what humans can conceptualize about phenomena like white holes, those elusive cosmic anomalies theorized as the reverse counterparts of black holes. Unlike black holes, which trap everything with their inescapable gravitational pull, white holes are hypothesized to spew out matter and energy, creating a paradoxical universe where the rules of physics often seem bent or outright broken. When AI models attempt to simulate these fabled entities, they often produce surreal, almost hallucinogenic images that challenge our understanding of reality itself. These visuals become a canvas of paradoxes, streams of luminescent matter flowing out of nowhere, fractal-like structures spiraling into empty voids, and luminous tunnels resembling cosmic geysers in an infinite, dreamlike state. What makes AI's interpretation of white holes so compelling is its capacity to synthesize known physics with a sense of the surreal, blurring the lines between scientific plausibility and abstract art. For example, an AI-generated visualization might show a vast, glowing void with radiant jets bursting outward, but the jets don't have clear origins. They seem to emerge from a shimmering, undefined boundary that oscillates between matter and energy, time and space. In some renditions, white holes appear as gigantic, shimmering mirrors reflecting other universes, hinting at the idea that they might connect disparate realms or serve as cosmic escape hatches. Here, the AI becomes a surrealist, embodying the cosmic questions that remain unanswered, creating visuals that are eerie yet mesmerizing, inviting wonder and skepticism simultaneously. The paradoxical nature of white holes becomes even more pronounced through AI's lens. These imagined cosmic objects, hotspots of theoretical physics, inherently challenge the second law of thermodynamics by seemingly reducing entropy, an idea that stretches the fabric of current scientific understanding. When AI visualizes such phenomena, images often include swirling, chaotic energy fields that seem to defy gravity or flow backward in time. Sometimes, AI experiments produce scenes of space illuminated by shimmering, fractal-like patterns, where matter spirals outward in a continuous, unstoppable cascade. This perpetual exodus of energy visually encapsulates the contradictions at play. A universe creating without ever needing to take in matter, constantly expelling what black holes purportedly swallow. Such visuals evoke images of cosmic loopholes, portals, and impossible geometries, pushing the observer to a brink of curiosity and skepticism. For AI, wrestling with the concept of white holes becomes an act of artistic exploration, portraying an impossibility that might, in some twisted universe, be undeniably real. AI-generated scenarios of white hole phenomena. In the realm of theoretical astrophysics, white holes are celestial enigmas, mathematical opposites of black holes, spewing matter and energy rather than consuming it. AI, with its boundless capacity for imagination and synthesis, ventures into visualizing these cosmic anomalies in ways that challenge our understanding of reality. When AI models are tasked with generating scenarios of white hole phenomena, they often conjure surreal visuals that defy conventional physics, blending the familiar with the profoundly strange. One common AI-generated scene depicts a luminous, spiraling vortex erupting from a point in space, an intense, radiant burst of light. Instead of the dark, inescapable trap of a black hole, this white hole emits streams of shimmering particles, akin to cosmic fireworks. These particles seem to dance and disperse, trailing iridescent arcs across the fabric of space-time. Yet, the paradox is stark. How can energy continuously escape gravity's pull without collapsing into a singularity? AI visualizations push boundaries here, presenting these phenomena as fluid, almost organic structures, like a geyser of light in an endless vacuum, challenging the static, mathematical images traditionally associated with white holes. Surreal visuals often feature a swirling, translucent barrier reminiscent of a glowing membrane, which appears to repel anything approaching it. Within this barrier, streams of matter, stars, planets, even entire galaxy clusters, are expelled at velocities that stretch beyond human comprehension. The more daring AI scenarios depict these expulsions as chaotic, vibrant storms, where the very fabric of space-time seems to ripple and fold under the influence of the white hole's energy outpour. These visuals evoke a feeling of witnessing an unnatural birth or an otherworldly fountain, embodying the paradox of how such an entity could exist without violating the laws of thermodynamics. AI's artistic interpretation emphasizes the surreal intersection of physics and fantasy, inverting our expectations of cosmic behavior. The deepest fascination in AI-driven imaginings lies in their depiction of the interaction between white holes and black holes, often portrayed as mirror images engaged in a cosmic dance. Some scenarios illustrate a hypothetical wormhole connecting a black hole and a white hole, oscillating with an eerie symmetry. As the black hole consumes and compresses, the white hole erupts across the universe, spewing out matter with wild abandon. In these AI visions, the boundary between the two becomes a swirling portal of light and shadow, suggesting an eternal cycle of creation and destruction that is both mesmerizing and mind-bending. These renderings remind us that, within the realm of imagination, the universe can be beautifully bizarre, where the impossible becomes a canvas for exploration and wonder. Implications for cosmology and universe models. The concept of a white hole, by defying the conventional laws of physics, invites a spectrum of radical possibilities for understanding our universe. Usually, black holes are viewed as cosmic sinkholes, regions where matter and information are pulled in irretrievably. White holes, in contrast, are hypothetical and theoretically perfect opposites, exuding matter and energy, but never accepting anything. If we entertain their existence, the implications for cosmology are staggering. They stretch the boundaries of traditional space-time models and challenge the very notion of causality. The idea that these exotic entities could be connected to phenomena, such as wormholes, a bridge potentially linking different parts of the cosmos or even separate universes, opens up scenarios where the fabric of space-time is far more intricate than our current understanding suggests. Visualizing a white hole engenders surreal, almost psychedelic, images, jets of luminous matter bursting forth from an infinitely dark void, creating an unsettling mirror of black holes. If some white holes exist at the core of these speculative structures, it raises the specter of universe creation events or ongoing cosmic rebirths. The possibility that our universe could be a white hole, spewing out matter from a multiversal abyss, fundamentally alters the narrative of cosmic origins. This perspective blurs the lines between beginning and end, singing a song of cyclic or even eternal rebirths in an endless dance of creation and destruction. Such models could also explain phenomena like the uniformity of the universe's temperature, as if the entire cosmos had a relationship to a singular, expansive white hole scenario at its inception. For cosmologists, white holes present a paradox that destabilizes many foundational assumptions. Does their existence imply that information could exit the universe in ways previously thought impossible? Might our universe itself be the aftermath of a white hole, a persistent fountain of matter and energy manifesting from what looks like nothingness? From a multiverse perspective, white holes could serve as portals or windows, offering glimpses into alternate realities where universes continuously cycle in and out of existence. These ideas push models beyond one-shot origins like the Big Bang into territories where the universe's birth is a continuous, perhaps even infinite, event, a braiding of multiple white and black holes across an unseen cosmic tapestry. In contemplating the implications of white holes for universe models, one must consider the profound tension they introduce between relativity, quantum mechanics, and thermodynamics. They challenge the arrow of time. What if the universe isn't an unfolding event driven by a linear progression, but a complex interchange, with white holes acting as cosmic fountains? Surreal visuals come into play. where the fabric of reality appears fractured or layered, with portals opening onto other realms. Embracing these radical ideas does more than stretch scientific imagination. It could provide the scaffolding for a unified theory that accounts for the birth, evolution, and potential multiversal connectivity of everything we observe. They compel us to rethink what possible truly means at the cosmic scale, compelling questions that revisit the core fabric of existence itself. Philosophical and ethical considerations. Diving into the concept of a white hole conjures a tapestry of profound philosophical dilemmas and ethical puzzles, each more surreal and paradoxical than the last. A white hole, regarded by some as the reverse of a black hole, ejects matter and energy rather than absorbing it, an eternal fountain of creation, defying conventional causal relationships. This inversion of natural law raises questions about the very nature of existence. If the universe can spawn matter from a point of seemingly nothingness, what does that say about creation itself? Does it challenge our understanding of causality, responsibility, or the meaning of origin? The notion that an entity could continuously produce matter without apparent cause surfaces as a paradox that unsettles not just physics, but the ethical frameworks built on cause and effect. Morally, the implications spiral into wild tangents. If a white hole bursts forth with objects, information, or even living beings, who bears responsibility for the consequences? Imagine a white hole spewing forth a vibrant, chaotic mess of life, some benevolent, some destructive. The idea of wielding such unbounded generativity forces us to reconsider notions of accountability. Does the white hole itself bear guilt for the chaos it unleashes, or do we assign moral weight to the entities that emerge? These questions are reminiscent of debates surrounding artificial intelligence that surpass human control. Powerful creators that could, without intent, reshape reality in unpredictable ways. The surreal visuals of a white hole, colors bleeding into an endless void, matter pouring out in a chaotic dance, only deepen the ethical conundrum, hinting at the potential for both miraculous creation and existential catastrophe. The ethical quandaries extend further when contemplating observer effects and the nature of knowledge. If a white hole exists and its outputs are impossible to fully observe or predict, does that render certain truths inherently unknowable? The very act of trying to understand such phenomena might itself alter their behavior, weaving a tapestry of observer-dependent reality reminiscent of quantum mechanics' notorious paradoxes. This could prompt us to question whether human morality can apply meaningfully within realms where cause and effect become so entangled that they defy linear understanding. The potential for a white hole to serve as a cosmic fountain of endless, unpredictable matter or information compels us to ask if humanity has the ethical right to intervene, manipulate, or even attempt to harness such entities, knowing that any action could result in unintended, possibly catastrophic consequences. In the end, contemplating a white hole doesn't only stretch our scientific imagination. It forces a confrontation with the limits of human comprehension and morals. To entertain these possibilities is to dance along the edges of chaos and creation, where the surreal visuals mimic internal paradoxes that linger in the mind's dark corridors. A universe that endlessly gives, with no apparent regard for fairness or harmony. Such considerations remind us that philosophy, ethics, and science are threads woven tightly in the fabric of understanding reality's most incomprehensible aspects, urging curiosity while cautioning us about the shadows cast by the impossible. Future directions in theoretical physics and AI collaboration. The interplay between artificial intelligence and theoretical physics is forging pathways into realms once confined to speculation, pushing the boundaries of understanding in ways previously seen as impossible. Machine learning models now assist in tackling the paradoxes that have perplexed physicists for decades, such as the black hole information paradox or the nature of space-time singularities, by analyzing vast datasets and generating hypotheses unfettered by human cognitive biases. AI systems excel at sifting through complex, multidimensional data, revealing subtle patterns that might hint at a coherent theory of quantum gravity or even suggesting entirely new frameworks that reconcile general relativity with quantum mechanics. The collaboration between AI and physicists isn't merely computational, it's deeply conceptual. Experimental ideas like simulating white holes or speculative structures like traversable wormholes are now examined through AI-enhanced simulations that combine classical algorithms with quantum-inspired models. These simulations often depict surreal visuals, mirages of cosmic halls, shimmering portals, or swirling vortexes, each representing potential states of space-time under extreme conditions. Such images serve as visual hypotheses, inviting physicists and philosophers alike to grapple with the impossible, to ask whether these constructs are mere mathematical artifacts or glimpses into a deeper reality. Looking ahead, future research trajectories involve integrating AI more intimately into the fabric of theoretical physics, where quantum computing interfaces with gravitational models. Imagine neural networks trained not just on existing physical laws, but on the principles of information theory itself, crafting new theories from the raw fabric of data, spotting anomalies or consistencies that a human mind might overlook. AI could potentially operate as a theoretical partner, capable of producing bizarre, counterintuitive solutions, like a digital Rorschach test, challenging our assumptions about the universe's structure. Such advances may lead to breakthroughs in understanding mysterious objects with surreal properties, like white holes which visibly spit out matter in ways that defy classical intuition, or multiverse models that extend beyond our observable universe. As AI's capacity to analyze multidimensional blackboard chaos expands, so too does its role in contemplating paradoxes, where classical physics clashes with quantum phenomena, and the logical boundaries of the cosmos seem to ripple and fracture. This dynamic synergy might, someday, generate models that seem more like vivid illusions than strict scientific explanations, ephemeral, glowing, painted across the fabric of what we consider reality itself. It's an era where boundaries dissolve, and science takes on a dreamlike quality. The impossible becomes a testing ground for AI's limitless potential to imagine, simulate, and perhaps even unravel the deepest riddles of the universe. Inside a white hole, where the usual flow of space-time reverses and the impossible becomes tangible, the mindscape unfolds in surreal bursts of vivid, often disorienting visuals. Unlike black holes, which swallow everything in their event horizons, white holes are hypothetical phenomena that eject matter and energy outward with no apparent end. Picture a rip in the fabric of reality, spewing streams of glowing particles that shimmer with strange, otherworldly hues, blues, violets, iridescent flashes, like cosmic fireworks set against an abyssal backdrop. These visuals defy ordinary physics, hinting at a universe where causality and temporal order collapse into a chaotic ballet of unpredictable explosions. One of the most paradoxical features of white holes is their inherent contradiction with the second law of thermodynamics. They appear to defy entropy, violently ejecting structured matter, while the universe tends toward disorder. In this realm, the flow of time feels inverted or altogether nonsensical, where past and future swirl together in a kaleidoscopic jumble. Imagine witnessing galaxies of melted stars pouring out of a shimmering void, only to see them instantly recombine into new celestial forms or vanish into the ether. It's a surreal cycle that challenges the notion of origin and destination, blurring the lines between creation and destruction in ways that stretch the logic of normal space-time. Visually, a white hole could resemble a cosmic fountain, a swirling, ever-expanding geyser of radiant energy. Instead of the dark maw of a black hole, this is a luminous, gushing core that spirals with infinite complexity, layers of shimmering plasma, fractal architectures, and impossible geometries. These visions evoke heightening curiosity and unease. What does it mean when, instead of absorbing, the universe simply disperses energy into the void. Such constructs compel speculation about their role in the universe's architecture, whether they serve as bridges to other dimensions or as cosmic mistakes woven into the fabric of reality. Their appearance teeters on the edge of the surreal and the scientifically plausible, a tantalizing glimpse into what might be just beyond the limits of comprehension. In contemplating a white hole, imagining its interior, if such a thing could be mapped, becomes an exercise in surrealism. Inside, evidence of collapsing and expanding structures coexists unnaturally. Matter might seem to stretch and fold in impossible ways, defying Euclidean geometry and material stability. The neural-like webs of quantum fields might ripple through the space, glowing with unnatural luminescence, flickering in and out of existence. These visuals serve as a reminder that, in the realm of pure imagination, the boundaries of physics are pliable. What seems impossible stretches into the realm of captivating, paradoxical beauty. Studying and visualizing these phenomena pushes the very imagination to its limits, creating a landscape where cosmic logic is fluid and the impossible is just another question waiting to be answered, or perhaps forever unanswerable. As we pull back from the surreal depths of this white hole, what lingers is the astonishing possibility that the universe itself might harbor hidden doorways to realms beyond our imagination, a paradox wrapped in shimmering, impossible visuals. AI's daring exploration into these artificial visions reminds us how much remains undiscovered, inviting us to question the very fabric of reality and the limits of our understanding. Imagine the wonders and mysteries still waiting to be uncovered, shimmering just beyond the horizon of current knowledge. If this glimpse into the impossible sparks your curiosity, stay tuned. There's so much more ahead, more worlds to explore, more paradoxes to unravel. Keep wondering, keep questioning, because the universe's greatest secrets might just be a curiosity away.